Hello everyone. Uh, so till now in this course we have been looking at combination circuits. We saw how the combination circuits are built using CMOS, how the delay is estimated. Now let's look at another class of circuits, sequential circuits, which are very integral part of any digital design. So in this during this lecture, we'll see how sequential elements are used in sequencing. We'll see two major types of sequential elements, latch and flip-flop. We'll see how they are designed using CMOS. We'll look at the delay of the delay parameters of a latch and flip-flop both. Now latch and flip-flop both have the concept of max delay and min delay. We'll look into that. Now wherever there are sequential elements, there is a clock. The clock comes into picture. So we'll look at the clock's skew, how important it is during the analysis of the delay. We'll touch upon time borrowing and we'll see a bit about two-phase clocking. The time borrowing, the delay concepts are just touched upon in this lecture. They will be explained and used in detail during unit 4 and 5, that is during synthesis and static timing analysis. But here we'll lay down the basis of these concepts. So let's look at what is sequencing, why do we need it in circuits. Now the major difference between combination and sequential logic is that for combination logic the current output depends only upon the input state at that moment. So if you change the inputs after some delay, inherent delay of the CMOS, the output will reflect that change. For example, for an AND gate, if both the inputs are 1, the output is 1. If you change one input to 0, the output will go to 0 after some finite amount of delay. A sequential logic, on the other hand, the output depends not only on the previous inputs, but also not only on the current input state, but also on what the input was before. So that is why sequential logic is used to separate the previous, current, and future events. These the outputs of sequential elements are called states or tokens. There are two very famous examples here. One is of a finite state machine, and there is a pipeline. So if you go back to your basic digital design, remember what an FSM was. An FSM is a set of sequential circuits representing a particular state. Now when these sequential circuits move from one state to other depending on what inputs we apply. So a finite FSM circuit is something like this. You have a bank of flip-flops, a bank of registers, and the output of these registers depends on the inputs and also on what all outputs are going. So it depends not only on the input state, the present input state, but also on what input was, what the state of this bank of registers was previously. As compared to an FSM, there is a circuit like pipelining where the data will just skip through different stages. So let's say this is stage 1, some processing happens during this phase, this combination logic, this is stage 2, this is stage 3, and so on. Now the question arises, why do we need sequencing at all? So let's say if the tokens or if the states of the combinatorial circuits move at constant speed, so all the parts in your design, then there is no need of sequencing because the sequencing is inherently being taken care of. For example, in fiber optics, the light pulses which are equivalent to tokens here are sent down an optical cable. The design itself guarantees that the next pulse is sent before the first peak is at the end of the cable. It will not happen that the input pulses will not reach the end of the cable out of order. So since this is guaranteed by the nature of the design itself, there is no need of a separate hardware to separate these pulses. Although the physical limitation posed by the effect of light dispersion So it's a minimum time between pulses, but otherwise no extra hardware is required. You can say this is an equivalent of wave pipelining in circuits. In case of digital design, this type of inherent capability is not there. That is why we need extra hardware to make sure that the tokens transfer from input to output side in order. So what this means is that we delay the fast tokens so that they don't catch the slow ones. This might be a bit confusing in theory, but we'll see a lot of practicals of this. And there's one more course of the computer architecture which deals very extensively into this, the pipelining inside a CPU design. So that will help in making this story very clear why sequencing is required. But otherwise, as we go on and see examples and synthesize them, you'll start appreciating this concept. Now, obviously, when we use any sequential element like a flip-flop or a latch to delay fast tokens, so that they move to exactly one stage in cycle, it will add some delay to the slow ones also, because they have to be also the flip-flops also have to be added to slow tokens. Now, this if we compare two circuits, one is wholly comprised of combination delay, and other is comprised of combination plus sequential. The one where combination plus sequential elements are used will be a bit slower than the earlier one. This type of overhead is called sequencing overhead. Some people also call this clocking overhead, because when we add sequential elements to design, we also have to add the clock. But it also applies to asynchronous circuits too. We might encounter one or two examples later. This is the inevitable side effect of maintaining sequence. When you want to maintain sequence, you have to make sure that the faster tokens do not overtake the slower tokens out of order. This is the essence of sequencing. Now let's look at the two basic sequencing elements, latch and a flip-flop. So a latch is a level sensitive device. On the other hand, a flip-flop is an edge triggered device. The most famous example of a latch is a D-latch. What a D-latch means is that the data appears on queue whenever clock is active. A flip-flop is usually made from two latches which are combined in a master-slave configuration. We call this a D flip-flop or a D register. Now, going back to basic digital design, we studied, if you remember, we studied a JK type or a T type registers also. But in today's design world, the D latch and the D flip-flop are the two most extensively used elements. Let's look at the timing diagrams of a latch. The latch is on the left hand side. The flip-flop is on the right hand side. A flip-flop can be the symbol of a flip-flop has a triangle attached to the clock wherever the clock connects to the rectangle. This differentiates between a latch and a flip-flop. So let's look at clock. So usually a clock in a design is mostly a free running clock. That means it has a certain frequency, and there's a high pulse, and there's a low pulse. So now, whenever clock goes high, let's say assume data to be like this, data to be changing like this. What happens to the output of a latch, and what happens to the output of a clock? Okay, now the latch functionality is such that whenever the clock is active, that is, we are assuming that the clock is active during the high phase, that is during the high pulse. Now in this phase, a latch is transparent. That means whatever happens on D will appear on Q after some delay. So we see here that D is going to 1, and then again D is going to 1, again going to 0. So this is propagated to Q. So Q goes to 1 and to 0 after some time. Now when the clock goes to 0, the closing edge of the clock, that is whenever the clock is going from high to low, this will close the latch. What it means is that whatever data is there in Q will be held. So any change on D during this period, during the clock low period, does not appear on Q. Let's revise again. During clock high period, during the clock high pulse, the latch is transparent. So latch behaves like a combination element or a buffer. Anything on D gets transferred onto Q. Whenever the clock goes to inactive state, whatever is the state of Q is held. On the other hand, a flip flop, whenever clock goes from 0 to 1, that is during a positive edge, in a positive edge triggered flip flop, whatever is on D passes on to Q. So now at this moment D is 0, so Q goes down to 0. With this arrow, the blue arrow shows the effect, the logic and the timing effect. That is, whenever clock goes to 1, whatever is D is transferred onto Q. So Q goes to 0 after some time, and then nothing happens on Q irrespective of whatever is happening on D during the high pulse or the low pulse. The next trigger will only come at the next positive edge of the clock, when again the D is 1, so Q goes to 1 after some time. So the difference is the latch is a level sensitive device and a flip flop is an edge triggered device. Let's look at how these two famous circuits are built using CMOS. This is a very basic latch, nothing but the clock is connected to gate. D and Q are connected to source and drain respectively. So this is, if you go back to the previous lecture, it is nothing but a pass transistor, just a pass transistor latch. Obviously, it is the smallest latch possible using NMOS or PMOS. What are the advantages? Obviously, it is very small and low clock load. We will look at what it is meant by low clock load. Just note that the clock, that is 5, has only one load, that is the gate of this transistor. The disadvantages, cons, many. Since it's a pass transistor, it will have a VT drop. It will be non-restoring because the output is not driven by VDD directly. Output is in fact driven by D. It will be back driving because D is connected to Q through the diffusion layer. The effect of this is that whatever noise appears on Q can be back driven to D. It is dynamic. We will look into what is dynamic, what does dynamic mean here. And the input is not connected to the D input is not connected to gate, rather it's connected to diffusion, which is not desirable most of the time. Now let's look at, in next few slides we'll look at the different improvements that have been done over this basic design. So improvement number 1, we replace a pass transistor by a transmission gate. So what we solve the case of VT drop here, since now we are using both PMOS and NMOS, so there is no VT drop. Now here note that the clock 5, earlier it was connected to just one gate input, now it's connected to 2 gate inputs, so the load is increasing on clock, and further it requires an inverted clock. Next improvement we do is that we added one inverter. From D to Q, we can add the inverter at the Q side or the D side of the transmission gate. Advantages, now D in the second case, in this case D is now connected to the gate and not to the diffusion. In this case Q bar is not connected to, is now connected to the drain, that is, it is being driven by VDD here in this case, so it is restoring. Q does not drive anything back to gate, back to D. So one of these two designs fixes, so for example design number 1 fixes the output noise sensitivity, since Q is directly driven by VDD or ground. The second circuit solves the diffusion input case. Obviously, in both these cases, we have the output is not available directly; it is available as an inverter. Output is inverted, right? Let's see one more improvement over this. Now what we do, okay, let's go back to previous circuit and see the state of X. Now the X will have some, the node X will have some capacitance with respect to ground or VDD depending on the logic level of X. Let's say the clock is 0. Whenever the clock is 0, this transmission gate is switched off. That means D is not connected to X. So the voltage level on X will start degrading over time. Now let's say you keep clock off for some big amount of time. The voltage value on X will start degrading across the capacitance with respect to ground or with respect to VDD. This is the case where we say that this circuit is dynamic in nature. That is, X, the node X is dynamic in nature. It may show some weakening of the logic level. Now in this circuit, what we do is we take the feedback from Q. We take the feedback from Q and feed it back into X. When does this happen? So there can be one case at a time. Whenever D is driving, this does not exist. This feedback part does not exist because the connection of transmission gate is complementary. So whenever clock is 1, this transmission gate is active. This is inactive. If you see, the clock is connected to the complement here. So D drives X. In the other case where the clock is off, so this gate is off and this is on. So now the Q is driving X. So at all times X is being driven. So that means that we try to restore the value on X on all times. So this circuit is static in nature. That means it is not dynamic. It is static. The back driving risk, negative is back driving risk because Q being ahead in the circuit is driving back X, but still it is an improvement over the earlier case. Static latches are now essential. We must make sure that the voltage levels do not degrade. If the voltage levels are degraded, it is very disadvantageous. That means any small noise can affect the functionality of the circuit. Next improvement, we buffer the input. Buffering the input will obviously fix the diffusion input. It is non-inverting. We do one more tiny improvement, is that what we do is, instead of compared to the previous circuit, instead of taking Q from now Q is feeding back into X here. Now instead of taking Q output here, in the next improvement we take Q from X. What does this do now? Is that it prevents the case of back driving. So Q is Q itself, the output itself is not driving back anything into the circuit. This is very desirable from the noise point of view again. So this is the most widely used latch design. This is very robust. Obviously, since we added about 4 inverters to the basic transmission gate design, it is pretty large. It is slow. FO4 here means fan out of 4. It has high clock loading. Now note here that clock here goes to 4 ports, 4 pins. So the loading is about 4 here, plus we need an inverter clock. But considering all the disadvantages, also this circuit is very robust. This is the most important thing in such design. Now this is one example of this slide is more or less a repetition where we remove the inverter from D. So to reduce the this can be one if we desire that, if we feel that a diffusion input will not cause a lot of problems in smaller designs or in older technologies, we could remove the inverter from D and make it a bit smaller. Obviously in this case the D is not buffered and connected to the signal. Now let's look at flip-flop. Again, going back to Morris Mano, basic digital design, a flip flop is made using two latches connected back to back together, with clock being inverted to the first one. This is called a master slave configuration. So this is an example of that. So in the first circuit, in this circuit, what we do is we connect. So this is one latch, this D to X. This is the Q of first latch, and this is again this part is the second latch. They are both connected together. The thing to note here is that this clock here and this clock here, they both are inverted. So the first latch gets a complementary clock when compared to the second latch. Now let's try to analyze the functionality of this. When we are comfortable with the understanding of the functionality of the first circuit, the second circuit is not much different from the first circuit. Whatever concepts we have applied earlier, that is how to make a robust latch, we have just converted the two latches here to the more robust form. Otherwise, first and second circuits are exactly same in terms of functionality. Now let's see, whenever clock is low, what happens when clock is low, or what happens when a clock is stable low or stable high. So when clock is stable low, stable 0, that means this particular transmission gate. So when let's see this. Okay, let's see the first case from D to X. What happens from D to X? So when pi, that is clock, is low, this part becomes active, D to X. So D to X is connected, but complementary X to Q is not connected. So whenever clock is low, there is no direct connection from D to Q. This is in fact the flip flop functionality. When clock is 1, X to Q is connected, or Q bar is connected, and D to X is not connected. So whenever the clock is either active low or active high, that is the stable case, there is no direct path from D to Q. Now what happens when clock goes from 0 to 1? So whenever clock goes from 0 to 1, so when it was 0, this was active, this particular part was active, so D was connected to X. So whatever is on D is on X. Now when it goes to 1, this latch closes and this latch starts turning on. So during the closure of this latch, whatever the value of was on X is retained, and since this latch is turned on, X is transferred to Q. So we go back and compare with the timing diagram. Whenever clock goes from 0 to 1, whatever is on D appears on Q, which is what happens in this case. So whenever it goes to 1, whatever is on D was transferred to X. When clock goes to 1, the value of X is held. When clock goes to 1, this part turns on and X is transferred on to Q. Exactly same thing happens in the second circuit. The only difference being we added a couple of feedbacks here to restore the value. We took the Q bar from the intermediate stage. We took Q here. We made sure that there is no Q or Q bar does not drive anything back into the circuit. So the second circuit is a more robust, more practical form of the clock. But to understand the functionality, the first circuit is different. Now there's one more. So now we saw a basic latch and a basic flip flop. Now what we do is we'll start adding different pins to a flip flop and see what happens. So one of the most famous pin is a clock enable or a data enable pin. So what enable means is that whenever enable is 0, we ignore the clock. That means we ignore what ignoring the clock means. We ignore what is on D. There are two ways of implementing enable in a latch or a flip flop. We add a mux. So this is the mux where enable is 0. The latch or a flip flop, the Q will hold it. So whenever enable is 0, the flop input will get whatever is on Q, so Q will maintain its value. Whenever enable is 1, it behaves like a normal flip-flop, that is D will drive Q on a clock trigger. Same thing with latch. The second implementation is adding the gating the enable with clock. So when we gate the enable with clock, when enable is 0, this is an AND gate. When enable is 0, the clock is always 0 on a latch or a flip-flop, so nothing happens. So the path from D to Q is off. Whenever clock is 1, it behaves like a normal latch or a flip-flop. Advantages of a MUX design, or let's say disadvantage. A MUX will, so this MUX is adding delay in the data path. So it will, in case of a latch, the D to Q delay is increased. However, for a clock gating case, the D to Q path remains same, but for a flip-flop case, the setup time will increase for enable. So enable is one more pin. We'll see what are setup hold times in case of flip-flop or latches, but just remember for now that the addition of enable pin on clock will increase the setup time, and it will increase the clock skew because we are adding one more gate into the clock. However, the second implementation, that is the clock gating, we will see lot more of this implementation. This clock gating is the most famous way to save power. We will see how. Now we add something called a reset to a flip-flop or a latch. Reset means that we want to reset the value on the output value. We want to reset all the flops or all the latches in the design. Then what do we do? So there are two types of reset. Resets, synchronous or asynchronous. Synchronous means that a reset will behave exactly like this, in the sense that reset will only affect the output whenever clock gets triggered in case of flip-flop. However, an asynchronous will behave as the name suggests. Whenever we assert reset, the Q will go to 0 irrespective of the state of the clock. So let's see how do we implement a reset for a latch and a flip-flop. So synchronous case is very simple. Since reset behaves exactly like D, we just gate D with reset. So whenever reset becomes 1, this node here becomes 0 and Q becomes 0 whenever the latch is transferred. So we see that similarly for flip-flop, we just add reset, we gate it with D, that's it. So whenever the clock trigger happens, this node will get transferred onto Q, and the Q will become 0, Q bar will become 1. For asynchronous case is a bit complex, is bit more complex as far as implementation goes. So we'll have to reset D, and we'll also have to reset the intermediate node. Why? Because we want to make sure that this Q goes to 0 irrespective of the state of the clock, and whenever the latch is transparent, this node also should not affect Q. So we add reset here also. So let's see what happens when reset goes to 1. When reset goes to 1, this node becomes 0 and this node becomes 0. So Q becomes 0. So even when the effect of reset goes and the clock is 1, we need D to become 1 to make Q 1. So if let's say this node was not reset, then what would have happened is that whenever clock comes, so this intermediate value, it can get transferred to Q. So to prevent this, we make this node so to make sure that reset works properly asynchronously, we have to make sure that this node here and this node here, these two nodes have to be reset. So we gate these 2 points with the reset. Same thing happens in a flop. A flop is nothing but master state configuration, so exactly same thing happens here. There is one more signal, very famous signal called set. So now we want to make sure that Q is 1 instead of 0. Exactly same concept as reset, only the gating will change. So this design implements both reset and set in a flip flop. I would urge all of you to go to Spice, implement this, and see the functionality for yourself. This is an asynchronous case, so you have to verify the functionality that whenever set
or reset, one of the set or reset is asserted, Q goes to the correct value irrespective of the state of the clock. Please note that it is invalid for both set and reset to be asserted together. It is not a valid case since you would want only one to happen. And you can also verify what happens in this case, what happens to Q in this case. Okay, so now we saw the design of a clock, we saw the design of the latch, how they are built. Now let's look at the sequencing method, that is, how are these elements connected together to make sure that sequencing is correct, plus what happens to the clock. Now there are three methods. First is flip-flops, second is using two-phase latches, third is using pulse latches. Now although design wise latches are simpler, in the sense that construction wise they are smaller, but when we want to use such elements in our design, the flops are much more simpler to handle, the timing relationships are much more clear, the clock network is much more simpler compared to latches. That is why the first method, that is using flip-flops and using this type of design, is the most popular way of sequencing. 2 and 3 from this course point of view are just academic in nature. We will never use two-phase latches or pulse latches in our design in this course. Maybe some of the design people, maybe some product companies use this kind of design in very specific cases, but otherwise almost 100% of the industry uses the pulse case. So I'll focus a lot on pulse case compared to cases 2 and 3. Right. Now let's look at a few things here. Let's look at the timing diagrams. What all timings we will consider when we'll go into the sequencing thing. Right. So a combination logic has two types of delays. One is the max delay, other is the min delay. That is how much time. So the time it takes from input to reach the output. This delay value can be of two types. One is the propagation delay, other is the contamination delay. When we go back, you have to go back a few lectures and see what is contamination delay. I'll just quickly tell. Contamination delay is the case where the delay of the combinational circuits is less compared to the usual case. This is the case where, let's say, for a 2-input NAND gate, both A and B are transitioning. So the effect is that the output gets the value much more sooner than the case where only one of them is transitioning. Of course, for this course, what I would request is that assume the logic propagation delay to be a type of a max delay. That means it is the maximum delay this combination logic can have. Consider TCD, the contamination delay, to be the minimum delay. That is, it is the minimum delay this combination logic can have. Apart from the clock, so for a flip-flop case, a flip-flop, since the trigger point is the clock, so the propagation delay of a flip-flop is calculated from whenever the clock rises to whenever the Q gets affected. So for a flip-flop, the delay reference point is always a clock. So this so you have a flop propagation delay clock to Q, and you have, so this is max delay again, and you have clock to Q contamination delay, which is the min delay. For latch, apart from the clock affecting Q, the data also affects Q whenever latch is transferred. So you have 4 types of delays. 2 are same as flops, that is clock to Q propagation and clock to Q contamination. Apart from there are 2 extra delays, which are D to Q propagation and D to Q contamination. These 2. So, but flops and latches have few extra delay values. These are not exactly delays; these are restrictions. So a flop, let's say, a flop is guaranteed to work only if data does not change in a window around this clock. So let's say the clock transitions here. So there is a window on both sides during which data should not change. Only then it is guaranteed that you will get correct D. So this window is called a setup hold window. Data should be stable at least some time before the clock edge. This minimum time constraint is called setup time. That is, data should be set up before the clock period, before the clock trigger edge comes, and this restrictive time is called setup time. Similarly, data should be held for some time after the clock edge has passed. This restriction is called the hold time. So for a case of a clock, the hold time and setup time are calculated from the trigger edge, that is the clock edge that triggers the event. For latch, it is always a closing edge. That means the edge that closes, the edge that latches D to Q, the D has to meet a setup and a hold window from that edge. So a combination logic does not have such a concept. A combination logic is purely a delay concept. Whatever happens on input appears sometime after on the output. For a sequential element, however, the input should be stable before the trigger edge. For a flip flop, it's always D. For a positive edge triggered flip flop, it is always the clock positive edge. For a level sensitive latch, that means which is transparent on high edge, it is always a negative edge. Now let's see how do we use these figures, these delay numbers, these delay variables to estimate the frequency of a design, or in other words, to see what will be the sequencing overhead. Now let's look at the flip flop case, the max delay case. Now this type of diagram and these equations you will encounter a lot of times in the next units, because this is the basis of calculating the frequency of a design. Now let's say there was no sequential element here, so this combination logic is the only thing present here. So the delay, we say that the delay of this combination logic, let's call it TPD. So without any sequential elements present, the delay would have been TPD, right? Now we added one flop here, one flop here. We added some sequential elements. Now what happens? So whenever let's say the frequency, the time period of clock TC, the TC is the time between the first edge and the second edge of the clock. Now everything should happen within this period. Everything should happen within this period. So now let's say whenever the clock's first edge comes, it takes some time. That is since we are talking about max delay, we will take all the max delays in the previous slide. The max delays are always the propagation delays, the min delays are contamination delays. So for max delay case, we will take, so the maximum delay this clock will have is TPCQ. So after let's say clock arrives on 0 time, Q1 changes at TPCQ, D2 changes at TPD plus TPCQ, and since this change here at D2 should be at least before the setup time here. So what I would say is the total delay of this circuit is TPCQ plus TPD plus T setup, and this total delay should obviously be less than the time period of the clock. This condition will make sure that your circuit works. Now let's see what the equation is. So take T setup plus TPCQ to this side and confirm that whatever we've understood is in fact this equation. So T setup plus TPCQ plus TPD, all these three combined together should be less than TP. Now TPD was the original combination logic delay, so we say that we rearrange the equation to and take T setup and TPCQ to this side. Now we see that the TPD, we have added these two. The T setup and TPCQ are only there because we added sequential elements here, flip-flop 1 and flip-flop 2. So we say that we are adding a sequencing overhead of T setup plus TPCQ. This equation is very important. We will revisit this many times. We will revisit this when we start synthesis and static timing analysis. So please take some time in understanding this. Even if it is not clear here, I'm sure that it will be clear in unit 4 and 5. Now let's look at what happens during two-phase latches. I'll not spend too much time here on this latch case, since it is not it is just a theoretical case. So what you could do is you could go back and write the equations on paper and understand how it works. So the two-phase latches, the concept is something like this. The clock of latch 1 and latch 2. So you have latch 1 and latch 3 are connected by same clock. Latch 2 clock does not overlap with latch 1 clock. So there are two clocks here. So you have phi 1 and phi 2. Now what happens? Now let's say phi 1 goes active. So L1 becomes transparent. So data at Q1 changes after PDQ. This PDQ. Data at D2 changes after TPD1. Now latch 2 again latch 2 becomes active here. So there's TPDQ again for latch 2, and again you have TPD2 of this combination logic 2. So data after D3, data at D3 changes after TPD1 plus TPDQ1 plus TPD1 plus TPDQ2 plus TPD2. Without the latches, the delay would have been TPD1 plus TPD2. So whatever we add here, so what is extra here? Nothing but the propagation delay of latch 1 and latch 2. In fact, this is the sequencing overhead, which is 2. We add 2 times the delay of a latch. Now please note here that there is no setup time constraint here. Why? Because the setup time for a latch is calculated from the closing edge. Here, this closing edge is not important at all. Why? Again, because we made phi 1 and phi 2 non-overlapping. We have made sure that the data at D2 changes before phi 2 opens. So we are not changing data on the closing edge. So there's no concept of setup time here in this case. Right. So let's go to again this type of design is very rare using all the latches. Flip flops are more preferred since sequencing is much more in control there. As you see that we use 2 clocks here. In a big design, let's say a design has a 100,000 sequential elements. Now 100,000 sequential elements, each of let's say are driven by a single clock. This is a very common case where a single clock drives thousands of clocks in a design. So there's a lot of clock overhead. Now compare this to let's say a flip flop will have a flip flop based design will just have 1 clock. So 1 clock goes to let's say multiple thousand clocks. If we replace that by latches and this scheme, we'll have to have 2 clocks. So adding 1 more clock adds again multiple thousand of overhead, right? Plus you have to make sure that phi 2 and phi 1 are non-overlapping, and that is not very easy in a big design. Owing to like clock goes to so many buffers, there's a lot of queue, so it is not easy to make sure that phi 2 and phi 1 are always non-overlapping. This is why this scheme is not very popular at a big level. This is the third scheme, which is pulse latches. So just note that we are looking at the max delay cases here. So all we are looking at is the propagation delays and not the contamination delays. Let's look at pulse latches. Again, we have 2 pulses here, so there will be a pulse here and there will be a pulse here. So there are 2 cases where pulse width is greater than the setup time or pulse width is less than the setup time. Now here the closing edge becomes important because this closing edge becomes important because it's just a pulse. So now let's say the pulse width is more than the setup time. So you will have D to Q. You have TPDQ, that is clock to Q. Sorry, data to Q. Plus you have the TPD, and this should be happened before the TC. The next pulse happens. So combining these two cases here, we say that the sequencing overhead is maxed of TPD or TTCQ, that is either contamination or the propagation delay, plus T setup. The setup time of this comes into picture, the closing edge comes into picture here, and minus the pulse width of 1, because here the pulse width is this pulse width is actually eating into the cycle timing. So everything should happen before that. But don't worry too much about the pulse latches case. It is rarely used. You will never see this again after in this course. Now let's look at the min delay. That is what happens. So when a clock has a max delay and a min delay. We saw the max delay case. Let's go back to the max delay. Now let's spend some time here. So let's look at this equation here. Now, what this equation does is it places a maximum timing constraint on this whole design. So what it says here is that the addition of the propagation delay of the clock plus the combination logic plus the setup time is kind of a delay in this case. This cannot be greater than the period or the frequency of the clock. What it means is that, let's say you have a big combination logic and plus you have some delay of the clock. What this does is it places the design, it tells us that there is a maximum frequency at which a design can operate. You cannot decrease TC without any limits. The maximum limit of TC, the maximum frequency at which you can operate your design, is 1 divided by TPD plus T setup plus TPD. So we call this as a max delay case since it applies a maximum constraint on your frequency. Now keeping that in mind, let's look at the min delay. So now the minimum delay of a clock, now in this case we will take TCQ. So the Q1 changes after TCQ, D2 changes after the minimum delay of combination logic, which is the TCD in this case. So now TCD plus TCQ should be such that they do. So this clock is actually the clock reaching flip-flop 2, F2. The delay change at D2 should happen in such that it meets the hold time requirement of this clock. So you have so what it means is that TCQ plus TCD should be greater than the T hold. So data should be kept held after T hold. When does data change? Data changes at TC, T contamination delay of the clock plus TCD of the combination logic. So TCD plus TCQ should be greater than T hold, which is again we arrange the equation and come up with this. So TCD plus TCQ is greater than T hold or greater than or equal to T hold. We rearrange the equation and get this. Again, the sequencing overhead is nothing but this TCQ. This is actually not a sequencing overhead, but what it does, it places a min timing requirement on the total delay. So what is the total delay here? The total delay is TCD plus TCQ, and it should at every time, all the times, it should be greater than the T hold. So now we see that the total delay, that is, the delay is actually nothing but the combination delay plus the sequential delay, should be at all times greater than the T hold and less than the time period of the clock adjusted by the setup time. So in fact now the delay of the circuit is limited by two cases, one is the max case, other is the min case. Also note that there is no, the clock frequency doesn't come into picture here. We go into depth in unit 5 on this equation. This equation is very important again, same as setup time equation. Similarly, we have the min delay case for two phase latches, and we have the min delay case for the pulse. So there is a min delay case of two phase latches. Again, it's very similar to the earlier case where we say that the delay here TCD1 plus CD2 and plus TCCQ plus T non overlap should be greater than the T hold requirement. The paradox here is that the hold time is reduced by the non overlap. The hold time applies twice each cycle, but only once for flops. But again, inside this flop is made up of two latches. You can verify this. No need to go deep into this paradox. It might be a bit confusing, but we clear that the one thing is clear that the equation of clocks are similar, simpler compared to latches. The clocking scheme again is simpler. You have known this is not there. You don't have to worry about overlapping or non-overlapping of clocks. So that is why a flip-flop based design is much more popular than latch-based design. So this is a case of pulse latches. I'll not go deep into this. There's no need for it now. Now let's touch upon a concept called time borrowing. Now, in a clock-based system, the data. Imagine a design like this. Let's go back to the slide. So a design like this. So data is launched onto the rising edge from flip-flop 1. It gets captured. D2 gets captured at F2 on this edge. This places a constraint here that everything that has to happen between these two edges. So data launches on one rising edge must set up, that is, it should become stable before setup time before the next rising edge. If the data arrives late, system fails. Obviously, you needed to capture the new data, but it is delayed. You could not capture it. If it arrives early, that means if it arrives even earlier than the hold time requirement of the next clock, then again the system fails. Or second case, it arrives somewhere in the middle. That is, it meets both the hold time requirement and the setup time requirement. So the time you have, the remaining time you have, is actually wasted. In the sense that what it again tells us that the fast tokens you slowed them, but then you had some margin available. That margin is wasted. So what it compares it compares a flop based system with a latch based system and tells us that if the data arrives early, but it still meets hold time requirement, time is wasted. Flops have hard edges. This is very important thing. You will notice in the earlier design that since the flop works on edges, nothing happens between the edges on the flop. So a flop has hard edges. Now compared to this, in a latch based system, a data can pass through a latch when transparent. What it means is that by playing with the clock, the overlapping or non-overlapping of the clocks, we can actually make sure that time is not wasted. This is called time borrowing. That is, we take the time from a fast circuit and give the time back to a slower circuit. Only if the only condition is that each loop should complete in one cycle. Let's look at one example. This is again a very this is now a common design feature where so what happens is that you have phi 1 and phi 2 again same case. Now in this case phi 1 and phi 2 are complementary of each other. So there is actually only one clock phi 1 and it is complementary and it is inverted and given to latch in the middle. So this latch will launch data. There will be a combination delay, and then we could borrow time from this circuit to this side. Why? Because let's say this is a slow circuit. This part is a slow circuit, so it takes a lot of time, and the data becomes stable somewhere here. But now the latch is transparent, so there is no data does not stop here. Data directly goes to this third latch, and let's say this when it wants to capture this, the data should remain stable, should come, let's say, somewhere around here. So even if this part of circuit is slow and this part of circuit is fast, we made sure that the time is not wasted, and in fact is perfectly utilized. The only requirement, the only constraint here is that the combined delay of combination logic 1 and combination logic 2 should at all costs be less than this time period. We'll again look more into detail. We'll look at a case where actually this is a clock, and this part is a latch. This is a very famous time borrowing case. We'll look into this into more detail in unit 5. This is again one more example of a circuit connected in loop. See this length is more here for a combination logic, so this means it's a slow logic. This is a fast logic. Again, this is B case is same as case A. Now, in all the previous examples, we were assuming that clock skew is 0. What it means is that the clock arrives on the flip flop 1 and flip flop 2 at the same time, but this is not exactly true. The clocks, since clocks go to thousands of flops in the design, not all the flops will get the clock at the same time. There will be some uncertainty in the arrival time. What it does, the uncertainty does to your design is that it decreases the maximum propagation delay, it increases the minimum contamination delay, it decreases time borrowing, so it affects negatively in all the cases. Let's see one case for flip flops. So what? So now there is you see this figure here. Now the clock arrival at each of the flip flops is actually uncertain in some limit. It is uncertain in this limit. So what it does is that it reduces the amount of margin you have. So what it does is that it adds to the propagation delay. So we saw that, so TPD plus TPCQ plus T setup. Now we add T skew here. So this T skew adds to the sequencing overhead. Similarly, this skew, however, it's shown positive here, but this skew can also be negative. That means it can also affect hold time negatively. So what happens? Let's say if the clock edge arrives early here, it is not good for setup case. If the clock edge arrives later here, it is not good for the hold case. We'll again see more details into this in unit 4 and 5. So let's there's a skew case for latches. You can go through the equations again, since it's not a very popular design. You can skip this. So let's look at what happens if setup time is violated. If setup time is violated, we saw that the setup time imposes a maximum performance limitation on the design. So if setup time is violated on a manufactured chip, you can actually reduce the frequency and still check if the chip is working. But if the hold time violates, you can do nothing. Chip will fail at any frequency, since hold time requirement is not the hold time constraint, the min delay constraint is not dependent on the frequency. So in fact, this is the reason we keep seeing. This is the reason why designers are more alert, more wary of the hold time cases when compared to setup time cases. So you have to make sure that hold meets in all the cases. What all cases means? It means that all the voltage in the voltage range for which the chip is specified. It means at all the corners of the temperature range. It meets in the slow process as well as fast process. We will see on the cases later. So this is the end of this. Let's summarize what we saw, what we learned in this section. We saw the design of the two basic sequencing elements, the latches and the flip flops. Flip flops are very easy to use. They are supported by all tools. We saw the three sequencing schemes. We saw flip flops, two-phase transparent latches, and pulse latches. Two-phase transparent latches have a problem of skew tolerance. You have to have non-overlapping clocks and time borrowing. Pulse latches are, in my experience, I haven't used pulse latches ever because this involves a completely different clock scheme. So I'll discount this case altogether. This table gives the sequencing overhead, sequencing overhead or the max delay, the minimum logic delay, and the time borrowing case. So you see for the flip flops, there is no such concept as time borrowing. There are some time borrowing equations for two-phase transparent latches and pulse latches. You can skip through this. So that is all for this lecture. Thank you.